Let's take a look at exercise 6 from section 4.2. Here we have a projectile launched upward at an acute angle, and the height of the projectile at a horizontal distance of x units from the launch site is given by the quadratic function h of x equals minus 1/2 g times the square of x over w naught plus v naught over w naught times x plus h naught, where g is acceleration due to gravity, w naught is horizontal initial velocity, v naught is vertical initial velocity, and h naught is initial height of the object. Complete parts A through C. So in part A, we want to find a formula that describes the horizontal distance from the launch point where the projectile is at a maximum height in terms of g, w naught, and v naught. Now, you'll recall that this is from the previous course, this is a quadratic function. If I were to expand this out, this would be h of x equals minus 1/2 g. And I need to square this x and this w naught. So in the denominator of g, I'll have the square of w naught. And this is the coefficient of x squared. Because remember, I'm going to be squaring this x and this w naught. And so notice this minus 1/2 g over w naught squared is my coefficient of x squared. And then the coefficient of x is already clear. That's v naught over w naught. And then the constant is my initial height, and that's h naught. All right, now the problem is asking us to describe the horizontal distance from the launch point where the projectile is at a maximum height. So when the height is max, whenever we have a quadratic function, the maximum, this function describes height. So height is maximum, or this quadratic function is at its maximum when x, which is my independent variable here, and basically we're going to think of this expression as ax squared plus bx plus c. The maximum occurs for a quadratic function when the independent variable is equal to negative b, that's the coefficient of my x, over 2 times a. A is the coefficient of x squared. So in this case, a and b are more complicated. Usually we are used to doing this when these are numbers, but in this case, notice a is not simply a number, but a is minus 1/2 g over w naught squared. B is v naught over w naught. So I'm doing something I already know, but the coefficients are just more complicated. So x, when the projectile is at its maximum height, the horizontal distance x is equal to negative v naught over w naught over 2 times negative 1/2 G over W naught squared. Alright, so first of all, notice these two negatives are going to make a positive. And then 2 times 1/2 simply gives me a 1. So I'm just going to put a slash through these to show that they multiply to give 1. So I'm now left with V naught over W naught. Notice this is a complex rational expression over G over W naught squared. Here, now this longest fraction bar is my main fraction bar, so I can also think of this as V naught over W naught divided by this main fraction bar. Any fraction bar means divided by, and so I'm splitting this at the main fraction bar. So this is divided by G over W naught squared, which is V naught over W naught times, so whenever we divide by a fraction, it's the same as multiplying times its reciprocal, W naught squared over G. So if I wanted to, I could write W naught squared as W naught times W naught. And then this W naught in the denominator divides into one of these W naughts in the numerator. And I am left with V naught W naught over G. So that's what X is equal to. That's the value of my horizontal distance when the projectile is at its maximum height. Okay, so at the maximum height, X is V naught W naught over G. So this is my horizontal distance when the projectile is at its maximum height. And notice this is the correct answer for part A. Now let's take a look at part B. So for part B, we want to find a formula for the maximum height of the projectile in terms of G, V naught, and H naught. All right, now we already found out that the maximum height happens when X is V naught W naught G over G. So we basically just need to evaluate the function when X is V naught W naught over G. So we're going to go in to our function. Now remember, here was our function. And wherever we see an X, we're going to replace it with V naught W naught over G. So remember, A was minus 1/2 G over W naught squared. And that was multiplied by X squared. But now X is being replaced by V naught W naught over G. Okay, if we go back to our function, B was V naught over W naught. That's multiplied times x, and we're replacing x with v naught w naught over g. And then our c was h naught. All right, so this is going to be the maximum height because that occurs when our independent variable x is v naught w naught over g. So let's simplify this. So we have negative 1/2 times g over w naught squared times, and we need to square this, v naught squared w naught squared over g squared. And let's write g squared as g times g plus v naught over w naught times v naught w naught over g plus h naught. All right, so here we're able to see we can do some simplifying. This square of w naught will divide into evenly, giving us 1, this w naught in the numerator. This g in the denominator divides and gives us 1 into this g in the numerator. So we are left with, from this part of the expression, minus 1/2 v naught squared over g. All right, and then here, this w naught divides into this w naught. So we're left with v naught squared over g, which we can multiply by 2 over 2, since we can always multiply by 1 and not change the value of something. So we see these are like terms. They both involve v naught squared over g. So if they have the same denominator, we can combine them. So we multiply that by 2 over 2, which is just multiplying by 1. 1 times a number always gives us the number. And then we still have the h naught. So negative 1/2 v naught squared g plus 2 over 2 v naught squared g just gives me 1 over 2 v naught squared g. Another way I can look at that is I'm combining the negative 1/2 and the plus 2 over 2, and the variable part of that is v naught squared over g. So you can look at it that way if that's a little more helpful. All right, and then this equals, so negative 1/2 plus 2/2 is simply 1/2. So this is 1/2 v naught squared over g plus h naught. And if you want to, 1 times v naught squared is v naught squared. 2 times g is 2g. You can write it like this. Okay, so when we go to look for our answer choices, notice that that's A in the answer choices for this problem, for this particular exercise. All right, and we see how we obtained that by looking at the work above. All right, let's look at part C. All right, and here's what we know already. We already found that when the projectile is at its maximum height, x, the horizontal distance, is v naught w naught over g, and h, the actual maximum height, is v naught squared over 2g plus h naught. And here, this is just a matter of plugging in values or substituting values, because we want G to be 32, W naught to be 51, V naught to be 51, and H naught to be 3. So we want to find the horizontal distance from the launch pad where the projectile is at a maximum height, and we also want to find the maximum height. So remember, the horizontal distance is H. So at the maximum height, the horizontal distance will be V naught is 51, W naught is 51, and G is 32. And we're told to round this to the nearest 2 decimal places. So we're just doing a very, very basic, simple calculation. Okay, so I plugged that into Mathematica, and I use the numerical approximation function, which is just called capital N. In Mathematica, when you use a function, you enclose it in square brackets. So I have 51 squared divided by 32, and it tells me it's 81.2813 approximately, and I want to round that to 2 decimal places, so 81.28. Alright, so the horizontal distance from the launch point where the projectile is at a maximum height is 81.28 units. And notice, I don't know, I wasn't told what the units of measure were. So whatever they are, whatever units were used to measure horizontal distance, it will be 81.28 of those units. So it could be, actually, it would have to be in feet, since gravitational acceleration is 32. That's actually 32 feet per second squared. And that's not something you need to know. That's just a fact. All right. Now, the problem also asks us, part C, asks us to actually find the max height. And we found in our previous calculations that max height was V naught squared over 2G plus H naught. So we simply substitute. So we know V naught is 51, so we're going to be squaring 51. We're going to be dividing that by 2 times G, which is 32. And we're going to be adding to that the initial height, which was 3, and actually this would be 3 feet, but the problem wasn't cluttered with units, so in the end we'll just say these are units. Alright, so let's use my Mathematica to do that calculation. So again, I'm going to use the numerical approximation, and I'm again squaring 51 and dividing that. Now, because this slanted division bar does not group, I have to actually group, because a horizontal fraction bar, as I've written it with my pen, does group. This slanted one that I'm using in my Mathematica here doesn't, so I have to group together the 2 times 32 with a parenthesis, and then I add 3, and I ask Mathematica to calculate that by holding shift and pushing enter. So I get 43.6406 as Mathematica's approximation, and I want to round that to 2 decimal places, so that would be 43.64 approximately. And even up here I should have had approximately. This is approximately equal to this. Alright, so the maximum height obtained by the projectile is 43.64 units when I round to 2 decimal places. And that is how I work problem 6 from section 4.2.